About refractive indices. We're going to use Snell's law in this. We're going to use the equation for critical angles and also just information about total internal reflection. So it combines everything. I thought it'd be a useful question. So this first question, it shows light going through oil and then refracting onto water and then refracting onto glass eventually. This line is what we call the normal, which is an imaginary line that meets the interface at 90 degrees. It's giving you refractive indices of oil, water and glass, and it's asking you to find the angle of refraction in the water. So here we can use Snell's law because we know the refractive index of oil is given as 1.47. We know the angle of incidence. We know the the refractive index of water is given as 1.33. So we can find the angle of refraction. So just quickly writing out Snell's law. By the way, it would help if you have your equation sheet with you. So maybe if you open that up in a different tab, you can use that to attempt the questions yourself. So refractive index of oil is 1.47 multiplied by sine of the angle of incidence is 44 is equal to the refractive index of water multiplied by sine of the angle of refraction, which we're looking for. And because I don't have space, I'm just going to write that. We're going to divide both sides by 1.33. So let me just get the eraser tool out. So we divide this side by 1.33. And then we do the inverse sine of both sides to get the value of theta. So we get that it's the inverse sine of all of this, which should get you to 50 degrees. I'm just going to double check. 1.47 sine 44 over 1.33. Yeah, it gets you to 50.15. So 50.2 degrees, which is about 50. Moving on then, it says the oil and the glass have the same refractive index, which is true. They both have 1.47. On the figure above, draw the path of the light ray after it strikes the boundary between the water and glass. So it's asking you to draw like this line here. Show the value of the angle of refraction in the glass. Well, because it has the same refractive index as oil, that means that it will make the same angle of refraction as this angle of incidence here. So we correctly found that this was 50.2 degrees. That would be the same with this one because of what we know about parallel lines and the alternate angle rule from GCSE maths. And so this angle of 44 degrees that we're going to draw, it has to be closer to the normal. And we also just want to label that as 44 degrees. That's fine for that. Explain why total internal reflection will not occur when the ray travels from water to glass. Well, there is two different ways of doing this. There is an equation for critical angles, but where n2 is the refractive index of where the light is going to, and n1 is the refractive index of where the light is coming from. But actually, there's an even simpler reason for this. It's because light has to travel from a higher to a lower refractive index for total internal reflection to take place in the first place. Whereas here, from water to glass, it's going from a lower to a higher. So that's your explanation for the mark. The fact that light must travel from a higher to a lower refractive index for total internal reflection. Sorry if you can hear the keyboard noise, by the way. You might want to skip 5-10 seconds. For total internal reflection. I'll just write TIL. Don't want to disturb you with this keyboard. And now we're going to talk about this part D of the question, calculate the critical angle. So that's where we use that formula that I was just mentioning. Where's the highlighter tool? Yeah, there you go. So because we're looking at the boundary between glass and air, it's going from glass to air. So remember, where it's going to is what we call N2, and where it's coming from is what we call N1. So in this case, it will be the refractive index of air, which it doesn't give in a question sometimes, because we always assume that it's 1, and we divide it by the refractive index of glass. Air is the only refractive index that we sort of assume. From here, you do the inverse sine on both sides, and you get the critical angle. Let's quickly do that. 42.9 degrees. Just as a rule of thumb, try to write to 3 significant figures. From there, that's pretty much the question done, but I wanted to ask a bonus question, because what we just found is that the angle of that's needed for total internal reflection is if it's bigger than 42.9 degrees between glass and air. But we also know that this angle that is coming in at is 44 degrees. So because the angle that is coming in at is 44 degrees, and that's bigger than the critical angle, which I've labeled with a theta c, and on top of that, because light is going from a higher to a lower refractive index when it goes from glass to air, what we can say is that total internal reflection will take place here. So only if both conditions are satisfied, then total internal reflection takes place, and it looks like this. So there's no more refraction taking place out into the air. Hopefully that made sense, and yeah, thanks for watching. If you enjoyed the video, please consider liking, subscribing, and I'll make at least one video like this every single day. So I'll see you soon. Bye.